research, and everyone invited to decide himself.
Okay.
Okay, let's start.
Let's start.
Please.
Okay, so as you mentioned, probably the most interesting thing I can tell you about is my research. So let's start with that. So first of all, I want to thank you for the invitation and the opportunity to present my research. The title of my talk is Non-Hermitian Symmetries and Topological Phases in Waveguide Optomechanics. This is not an easy title to digest. So in order to bring everyone to the same page, we will start fast and slowly increase the pace. Since these days all seminars are recorded, it became harder to recycle the jokes. But those of you who watch the talk for the first time may well still find them funny. So this is the picture of the Advanced Science Research Center in Upper Manhattan, where the research group I'm working with is located. And this is Ariel University, where this seminar is taking place. I'm quite sure that this is not the electrical engineering building, but this is the one that keeps popping up when you search on Google. So this is the most photogenic one, I guess. Well, in normal times, this is where we would be convening, but nowadays we have to settle for online meetings. So let us take a peek at some of the technology that enables this magic. While all social implications are still unclear, we would all agree that information and communications technologies have revolutionized modern society. Zoom, of course, is not the only social application out there. There are many others. I am not an expert on any of those. As a matter of fact, I didn't even have a smartphone until a couple of years ago. So this data-intensive application within your palm's reach, combined with the growing utilization of cloud computing, causing data traffic congestion in the supporting infrastructure. In fact, the ICT traffic volume has tripled in the last 5 years, representing a staggering compound annual growth rate of 27%. And this is not including last year, which probably grew much larger. Maybe not in this forum, but people are not generally aware what major role photonics plays in enabling these technologies. While information storage and logical processing are dominated by electronics, photons are the carriers of choice for information exchange between distant nodes of the network. When it comes to optical communication, two principal technological marvels stand out. The first one is the optical fiber. It has extremely low losses. It is very thin as a human hair, and very cheap. It forms the backbone of optical network, both inland and across oceans. This image is taken from a New York Times article about the deployment of fiber optic submarine cables. They ironically allegorize that the data is not in the cloud, as one might think, but it is rather in the ocean. The irony is actually double, as they fail to stress that optical fibers don't store data, but rather carry it from one place to another at the speed of light. Unless they were referring to underwater data centers. Anyway, the second technological marvel is integrated photonics, which enables high-speed optical communication at the rack, the board, and even at the chip levels. The transmission density, much like the ICT traffic, is also growing exponentially. Optical transceivers of hundreds of gigabits per second and millimetric sizes are already commercially available. Let us now take a brief look at several multiplexing architectures that give pushback on the optical transport capacity crunch. The first one is multi-core fibers, with which I worked intensively during my graduate studies. These fibers support large number of spatial channels and come in all shapes and sizes, practically allowing the degrees of freedom needed to design the communication link according to desired specifications. This may include crosstalk, intermodal or polarization dispersion, mechanical properties, etc. These systems, more widely known as dense spatial division multiplexing, already some years ago were shown to transmit petabits per second of information over a single strand of fiber. And they continue to push forward. Just recently, a fiber with 228 spatial channels was fabricated and evaluated for its transmission properties. While originally developed to increase the capacity of fiber communication, smart people found other interesting applications for multi-core fibers, such as microwave photonic filters, true time delay elements, optoelectronic oscillators, shape sensors, where by measuring the strain in each core, the fiber shape can be reconstructed. And the increasing availability of these fibers has also spurred a lot of basic research. For example, the theoretical study of the dynamics of discrete optical vortices. Another principal multiplexing architecture is wavelength division multiplexing. I will now shortly discuss one of our recent works to give you an example of how WDM is realized in a photonic integrated circuit. The principle of digital filtering gave us the inspiration to design the network of cascaded unbalanced Mach-Zehnder interferometers with nested ring resonators, which effectively realize 8 distinct autoregressive moving average bandpass filters at the 8 output ports of this device. In order to optimize the transfer function of these filters, we had to precisely control the optical phase delays of the interferometers arms and ring circumferences. The required accuracies, however, cannot be achieved with fabrication tolerances of standard silicon photonic waveguide alone. To address this challenge, we used the following post-fabrication trimming technique. We deposited patches of a thin layer of chalcogenide glass on top of the silicon waveguide. Then we selectively illuminated these photosensitive upper cladding layers with intense laser beam in the near infrared. This results in a chemical reaction known as photodarkening, in which the refractive index is increased. Or the layer can be completely removed in the process of mass transfer if the intensity of the laser is high enough. We control the exposure by monitoring the filter's response and comparing with model. We were able to obtain maximally flat bandpass filters with ultra narrow channel spacing of 70 GHz and strong out-of-band rejection. We also characterized the device performance using 40 gigabits per second dense WDM data streams, which showed high spectral efficiency of over 2 bits per second per hertz. Two important notes. First, when properly packaged, the device response remains stable over months. And second, while the prototype samples were fabricated in-house, the final devices were fabricated at Tower Jet Semiconductors. I emphasize this because most of the photonic integrated circuits I intend to work with in my group can readily be obtained nowadays from foundry services providers, which gives a great deal of flexibility to research in this field. Next generation optical communication systems with capacities exceeding petabits per second will comprise thousands of wavelength spatial channels. High fidelity transmission of information down these densely integrated waveguiding structures faces monumental challenges. And at the same time, solving these technological problems also holds great promise for many novel applications, as I will show further in the presentation. The challenges in the spatial domain arise from the tighter field confinement, which increases the sensitivity to the inevitable structural imperfections and results in enhanced scattering when light propagates through. Apart from the obvious detrimental effect of radiative losses, disorder-induced scattering also enhances intermodal coupling across DSDM channels. Furthermore, thermally excited acoustic phonons can give rise to dynamic optomechanical crosstalk across larger number of channels. There is also the danger of reaching the damage threshold of SDM fiber amplifiers, for example. In the frequency domain, High spectral density transmission is also compromised by the increasing linear crosstalk. Moreover, increasing optical confinement also intensifies nonlinear wave mixing between distinct spectral modes. Remarkably, the powerful DSP electronics mitigates most of the detrimental crosstalk effects in classical communication systems using techniques such as MIMO. Nonetheless, there remain several frontiers, such as optical networking and microwave photonics, where in situ control of wave propagation and scattering is necessary. And finally, although optics doesn't really put up a fight when it comes to classical information processing and storage, due to the weak interaction between photons, some applications for which the nature of optical effects is at the heart of their operation principle still present interesting research challenges. And for those of you who don't find the above opportunities appealing enough, photonics also plays a major role in the second quantum revolution. Here, the role of the photons is twofold. First, much like in classical communications, optical photons are the carriers of choice for information exchange between distance nodes in a quantum network. Quantum key distribution at megabits per second rates was already successfully transmitted over dozens of kilometers of optical fiber simultaneously with conventional WDM data streams. The use of multi-core fibers for increasing the secure key rate at QKD systems is also being explored in recent years. These trends are expected to continue, as no one is planning on building a new network infrastructure or spare some dark fibers for the quantum internet. Unfortunately, standard crosstalk mitigation techniques are not suitable for demultiplexing quantum information due to the signal-to-noise ratio requirements of DSP processing. Another field that is taking off rapidly is integrated photonic quantum computing. Unlike in communications, in computation, we actually do want the photons to interact. However, even the strongest nonlinearities in standard optical materials are nowhere near strong enough to support pseudo-deterministic photonic quantum computation. Probabilistic manipulation of photonic states using standard linear optics elements is nonetheless possible, albeit at the expense of huge overhead in the required resources. Just by looking at several representative figure of merit requirements listed here, the scale of the challenge becomes apparent. Most interestingly, however, is that even a small increase in the success probability of each gate operation can significantly reduce the resource overhead. This notion is what drives the current efforts to enhance the nonlinear effects in integrated photonic platforms. Parallel efforts for scaling up these systems focus on increasing entanglement dimensionality and active multiplexing of photons. Finally, nonlinear interactions are also key ingredients for precise manipulation of frequency encoded qubits. Specifically of interest to us is that these architectures are compatible with single mode fibers and show superior multiplexing scalability using nonlinear wave mixing. So, if to summarize the many motivation slides in 2 bullets, first, we want to robustly control the photonic degrees of freedom in densely integrated waveguiding structures. And to achieve that, we prefer to use the existing photonic infrastructure or with as little modifications as possible. Since by now you must have forgotten the title, but it includes a hint on the mechanism that can provide unique handles on the problem. I will now introduce the optomechanical waveguiding and interaction. The two-wave phenomena must interact, otherwise they are not useful for information processing. Let's start with optical fibers. It is a known fact that fibers guide light. Here you can see the electric field profile of the fundamental mode of a standard telecom grade fiber, As expected, the light is confined to the core. A less commonly known fact is that fiber structures also guide acoustic waves. For the case where there is no plastic jacket covering the fiber, the acoustic waveguide is simply defined by the cladding boundary. There exists a rich zoology of elastic waves. For example, almost entirely longitudinal modes, which either co-propagate or counter-propagate with the optical modes. Unlike longitudinal waves, which are mainly confined to the core region, radial waves span the entire fiber cladding. The colors here represent the radial displacement. There are also other types of acoustic modes supported by the fiber geometry, such as torsional and flexural waves, not shown here. As we said, the two-wave phenomena interact. Let's first explore the mechanisms of optical stimulation of elastic waves. In standard optical fibers, the dominant mechanism through which light can be used to generate pressure is electrostriction. In the electrics, electrostrictive force arises when the matter is exposed to electric field. Its magnitude is proportional to the gradient of the electrical energy. If we strictly consider stimulation within the fiber, only the first term here has significant contribution. Otherwise, if the dielectric constant is not homogeneous, its gradient should be considered as well. The exerted force, in turn, perturbs the material density. The evolution of this mechanical disturbance is governed by the acoustic wave equation, whose driving force, in our case, is provided by the optical fields through electrostriction. There are other ways to optically generate elastic waves. For example, through photothermoelastic effect, where the sound waves are driven by the absorption and subsequent thermalization of the optical energy, leading to temperature and hence to density variations within the medium. Optical fibers are famous for their extremely high transparency. Therefore, this effect is negligible. However, we employ this mechanism in integrated devices, as we will show shortly. There is also the radiation pressure effect, which kicks in sub-wavelength scales. Therefore, is irrelevant in our geometries. A complementary effect to optical stimulation of elastic waves is the diffraction of light by sound waves. The dominant physical mechanism in optical fibers is photoelasticity. Through photoelasticity, the mechanical strain induces perturbation in the dielectric constant of the medium. For the case of amorphous materials, such as silica, this tensor equation reduces to a simple proportionality relation, which is captured by the constant gamma E. This additional nonlinear polarization drives the optical wave equation as long as phase matching conditions, which we'll shortly explore, are satisfied. The effect of moving boundaries associated with radiation pressure is also negligible in fiber geometries. Two principal factors determine the strengths of the acousto-optic interaction. The first one is phase matching. This can be simply explained by using a dispersion diagram. Fibers support only two directions of optical propagation, forward and backward. Let's consider here the case of forward scattering. Please note that we are not concerned with phase matching conditions in the transverse direction, since the solution of the acoustic wave equation takes the form of standing waves. If we look at the axial dispersion curves of radial acoustic modes, we can identify the crossings at which acoustic axial phase velocity equals that of the optical mode. These discrete modes are the only ones that satisfy the phase matching condition for forward scattering. Therefore, an acoustic mode can be stimulated by a pair of properly detuned co-propagating optical waves, and the same acoustic modes can also be used to couple between the optical tones. Another important factor for efficient interaction is the spatial overlap. This very physically intuitive statement is mathematically manifested through the overlap integral formalism. The electrostrictive driving force has to overlap with the displacement profile to obtain efficient acoustic stimulation. And the refractive index perturbation has to overlap with the optical mode to obtain efficient scattering for the optical wave. In this example, you can see how two optically isolated cores of a multicore fiber can exchange information through acoustics. Similar physical principles can also be employed in integrated optomechanical waveguides, which is currently a very vibrant field of research. Unfortunately, standard silicon on-insulator photonic devices do not guide sound. Elastic waves driven in the high stiffness silicon waveguide rapidly radiate into the silica substrate. Two principal mitigation pathways are considered by the community. The first one is removing the substrate and leaving the optically guiding core layer suspended by tethers. These membranes support guided and elastic waves with shear and flexural character, some of which can mediate transfer of energy between optical modes. An alternative solution is to replace the silicon with soft chalcogenide glass, which has high refractive index and relatively low stiffness, thus allowing the confinement of both optical and elastic waves by total internal reflection. The second approach is the introduction of surface acoustic waves into photonic circuits. The most standard techniques rely on electrical excitation of surface waves in optical grade piezoelectrics. These material platforms have very large electromechanical transduction efficiency and also support optical wave guiding. Lastly, as a consequence of the optomechanical coupling that is designed to take place in the waveguide core, the radio frequency information is imprinted on the optical carrier. We took this principle one step further and showed in a recent publication that surface acoustic waves can also be generated in a standard silicon device layer through absorption of modulated pump light in metallic gratings. The acoustic waves are detected via photoelastic modulation of an optical probe, which propagates in a standard SOI waveguide. The photothermomechanical transduction efficiency is still low relative to piezoelectric actuation, but strategies to increase the efficiency are currently under study. One last important note. In both of these SAW devices, the generation of acoustic waves and the optical scattering processes do not spatially overlap. Therefore, the systems on the right lack the positive feedback needed for self-amplification of both the optical and acoustic fields. The systems on the left, on the other hand, do support stimulated Brillouin scattering, similarly to optical fibers. It is now apparent to you that optomechanics can spontaneously mix spectral or spatial channels, or it can be intentionally introduced to couple degrees of freedom that are otherwise orthogonal, and can be applied dynamically without resorting to structural modifications. Since practical systems of interest comprise thousands of coupled modes, it is useful to characterize their collective behavior using the tools of solid-state physics. Let's start with the short association game. What the Schrödinger cat state of a quantum particle and Fresnel diffraction pattern of light have in common? Well, they are both solutions of two isomorphic equations, the Schrödinger equation and the Paraxial-Helmholtz equation. What this implies is that the propagation of light in space is governed by the same equation as the evolution of the wave function of a quantum particle in time, subject to the approximations of the model. Here we identified that the refractive index plays the role of an effective potential in the optical wave equation. Similar analogy can be observed in the acoustic diffraction as well. The highlight of this result is that these effective optical or acoustic potentials can be spatially distributed arbitrarily. They can take any sign or even be complex. They can be time dependent or axial dependent in our case. And finally, we can use this principle to emulate artificial gauges that do not necessarily exist in nature. Indeed, these analogies paved the way for a burst of research activity in the study of topological quantum mechanical effects in classical wave physics. Just to give you a sneak peek at a few examples. Here, the analogy with one-dimensional quasicrystals enabled adiabatic pumping via topologically protected boundary states in a photonic waveguide array. In another example, an array of evanescently coupled helical waveguide arranged in a honeycomb lattice was used to emulate Fouquet topological insulators, which feature one-way edge states that are topologically protected from scattering. And similar principles were also demonstrated in acoustic systems. What most amazes me, however, is that these approximations also hold for non-classical states of light, which provides tool for the design of robust quantum circuits. Interaction with acoustic phonons can be used for dynamic control of the effective potential for photons, namely for amplification or depletion, coupling, and time modulation of a chosen set of spectral or special optical modes. I think that what stands behind these words is best captured in the following phasor diagram. It describes the equivalent nonlinear coefficients that govern the evolution of two optical probe waves. One is red-shifted relative to the pumps, and the other one is blue-shifted, denoted here by Stokes and anti-Stokes. The nonlinearity is created by two strong optical pumps through forward stimulated Brillouin scattering. The two pumps are assumed to be undepleted. In fact, if not stated otherwise, for the rest of the talk, we will limit the discussion to linearized interactions. What this graph shows is that by controlling the detuning between the pumps, the real and imaginary parts of the nonlinear coefficient can be modified. Photons and phonons can switch roles. In this example, the optically induced radiation pressure served as a synthetic gauge for phonons in coupled optomechanical crystal cavities. I also recently noticed a publication where they show the design of mod multiplexer in silicon for both guided optical and acoustic waves. Such platform can efficiently multiplex electrostrictively or photothermally excited acoustic waves, and potentially support future studies of mixed photonic and phononic states in Brillouin active waveguides. Let's take a look at some specific examples where we create synthetic gauge fields for photons using optomechanics in standard waveguide geometries. The simplest model to realize topological defect states is in one dimension is the SSH dimer chain that was originally used to describe the dimerization of a polyacetylene chain with open boundary conditions. In this example, you see they realize the topologically protected transport in a photonic system. They show that a topological defect can exist at the interface between two silicon waveguide dimer chains with different topological invariants. We wondered whether such dynamics can take place in the frequency domain in a standard fiber with optomechanical coupling. we assumed a two-mode optical waveguide, where dimerized coupling between mode alternating tones can be established through two counterpropagating acoustic modes of different intensities. Such acoustic modes can be generated by 4 strong optical pumps through intermodal Brillouin scattering, as shown in the dispersion diagrams on the right. If we look at the eigenmode profiles, we see a trivial distribution as expected in such system. The question now was how to define a boundary and create a defect without resorting to dispersion engineering through structural or material modifications in the waveguide. Our solution was to introduce gain through backward Brillouin scattering. What we got is a two-mode wide topological interface defect. Here we see that above certain popping threshold, a defect state is formed in the bandgap. The bifurcation you see is associated with parity time symmetry breaking in non-conserving systems. We will explain how to treat it in the non-Hermitian framework in the few slides. Also, in the eigenmode spectra, we can see the formation of the two-mode wide topological interface state at the center site. We also observed in simulation that this defect state is robust against disorder by simply adding noise to the two acoustic tones that realize the coupling or to the one that realizes the gain. The configuration we propose here can be simply realized in a commercially available photonic crystal fiber using interpolarization Brillouin scattering and torsional radial acoustic modes, as in this example. Our system manifests similar features to a non-Hermitian SSH system with alternating loss that was realized using waveguides inscribed into fused silica glass, except that our system is realized using off-the-shelf components and can be reconfigured at will. Another useful concept that I want to introduce is called synthetic dimensions. The synthetic dimension can practically be any degree of freedom: frequency mode, spatial mode, polarization mode, orbital angular momentum, etc. Let's take a look at yet another simple example, where a synthetic frequency dimension is used to realize an effective magnetic field in a two-dimensional space spanned by the frequency modes and 6 coupled resonators. The resonators are evanescently coupled, and the frequency coupling is realized via electro-optic modulation. The hopping phases are properly chosen to implement what is known as the Landau gauge for a uniform magnetic field. The dynamics of this system is approximately captured by the following tight-binding Hamiltonian. Here is the characteristic band diagram with one-way edge states that lie within the band gap, as we already saw several times. Please note that this is the projection of a two-dimensional band structure of the entire system. Also, the number of resonators used to generate this plot is much larger than 6, but the principle holds nonetheless. Here, you see the steady-state intensity distribution in the systems when the light is coupled to the leftmost resonator. The photons can be thought of effectively to propagate along the edge of the synthetic structure. Such system can be used, for example, for high-efficiency generation of high-order sidebands. We showed that similar system dynamics can be achieved without external electro-optic modulators in an all-optical configuration. We use traveling wave optomechanical cross-phase modulation in multicore fibers. The radial acoustic disturbance has originated in the central core and reached all other 6 outer cores, providing the necessary modulation. The interconnect lengths were properly adjusted to account for the phase shifts. Here we see the simulation results. For in-band excitation, the steady-state intensity is distributed in a trivial manner. But when we excite in the bandgap, it is reminiscent of the characteristic transport along topological edge states. As promised, I will now introduce the principles of non-Hermitian physics and some of its interesting consequences. Without explicitly stating this, but for the most part, we thus far considered only Hermitian systems, with no loss or gain and dissipative coupling. And dispersive coupling, I apologize. While this may hold for optical fibers, losses are a central issue in photonic integrated circuits, and most certainly not true if gain is introduced into the system. Most practical systems are therefore non-conserving and need to be treated in the framework of non-Hermitian physics. Don't get me wrong, the mathematical framework does not suddenly turn loss into a desired feature. It rather offers unique handles on the problems involved. As postulated by Carl Bender in his seminal paper from some 20 years ago, one of the central results of the non-Hermitian theory is that some Hamiltonians, despite being non-Hermitian, may still possess a real spectrum if they obey parity time symmetry. The Hamiltonian is called PT symmetric if it is invariant under the combined action of the parity inversion and time reversal operators. For many years, physicists struggled to find a physical system that obeys this symmetry. Until some 10 years ago, it was noticed that it can be realized using complex optical potentials. To put it in simple words, the real part of the refractive index should be an even function of the spatial coordinate, and the imaginary part, which is gain or loss, should be odd. Commuting with the PT operator is a necessary condition, but it is not sufficient to ensure a real spectrum. A real spectrum is obtained only when the PT phase is exact. Otherwise, the eigenvalue spectrum is imaginary. The phase transition occurs at a singularity known as the exceptional point, where both the eigenvalues and eigenvectors coalesce and become degenerate. Using this framework, we can now extend our discussions to systems with loss, gain, or dissipative coupling, or any combination thereof. There have been many beautiful demonstrations of this principle and their applications in photonics over the recent years. Common to all examples here is that they employed nanofabrication techniques and require tight tolerance control of the resonance frequency, gain, loss, or coupling. We, on the other hand, showed that these effects can be observed in a standard optical fiber using the optomechanical effects we came to love so much. We employed a scheme known as Brillouin-enhanced 4V mixing. Our degrees of freedom are two continuous wave prop tones, A1 and A2, marked here in red, separated by the frequency delta n. They are amplified and dissipatively coupled by a pair of counter-propagating Brillouin palm tones, marked here in blue, separated by the same frequency delta n. Maximum gain and coupling is achieved for a palm prompt separation by the Brillouin frequency shift of the fiber. The evolution of the two prop tones is governed by the following Schrödinger-like equation. Here, H naught is the anti-PT symmetric Hamiltonian of the system, which depends on the detuning delta n and palm's power. Let's take a brief look at the very simplified schematic illustration of the experimental setup. Important to note that all optical signals used in the system were drawn from a single narrowband laser source in the telecom wavelength range. The magnitudes and phases of the two input probe tones could be controlled independently by an arbitrary waveform generator. The fiber under test was a 10-meter long, commercially available single-mode fiber. Following the Brillouin-enhanced 4V mixing process, the output probe waves were detected by a coherent photoreceiver, recovering their amplitude and phases. As you can see, the retrieved eigenvalue spectrum agrees well with theory, and we are able to observe a phase transition between antiPT symmetric and broken symmetry regimes with large precision. We also observed the exceptional point and the enhanced response to changes in the detuning between the two probe tones in agreement with our analytical predictions. The enhanced sensitivity, however, is not very useful for environmental sensing purposes. It simply sets the limit on system stability. Now I will show that we also observe enhanced spectral response to changes in the Brillouin frequency shift, which is the single most important mechanism in distributed fiber sensing. The modified Hamiltonian can now be approximated in terms of a first-order perturbation correction as follows. Delta B here marks the normalized detuning from the Brillouin resonance of the fiber. The eigenvalues of the modified Hamiltonian can be written as follows and visualized by what is known as Riemann surfaces. When we experimentally characterize the eigenvalue spectrum as a function of the Brillouin detuning in the vicinity of the exceptional point, we also observed enhanced response to small-scale changes in the Brillouin frequency shift. Remarkably, the eigenvalue splitting has a square root dependence on the environmental perturbation as well, with potential opportunities for Brillouin sensing applications. Another useful feature of non-Hermitian system is asymmetric mode switching when performing a loop in the parameter space around the exceptional point. As you can see here on the right, the Riemann surfaces in our system exhibit a branch point topological structure around the exceptional point, which features a discontinuity in the broken PT phase. Therefore, for the eigenvalues to continuously change across this line, they have to switch their values. We expect one swap of the eigenvalues for one turn around the exceptional point. And indeed, this is what we see experimentally. However, we did not directly observe swapping since we measured the eigenmodes in a stationary manner. A robust topological model transfer is nonetheless possible in our system if we continuously change the parameters under a single excitation. For this, we will need to pulse the probe modes. We will also have to tailor the pump power and frequency to execute a closed control loop in the parameter space. To do it adiabatically, we will also need a longer fiber, which makes it challenging to maintain the polarization. Therefore, it offers no practical advantage to build such a system in the fiber. However, it makes much more sense to harness the recent progress in the design and fabrication capabilities of Brillouin active devices to precisely control the acoustic dispersion and dissipation along the waveguide through structural modifications. The design strategy is quite simple. As we already said, we want to sculpt the parameter space to execute a loop around the exceptional point under a single excitation. We want the loop lengths to be longer than the inverse of the normalized gain difference between the eigenmodes. This is just the manifestation of the adiabatic limit in our system. It is required to observe significant energy exchange between the eigenmodes. And needless to say, we must pump below the device damage threshold. We expect that such a design will possess the following features. First of all, it will be optically transparent when the Brillouin pulses are turned off. It will be non-reciprocal by design because of the phase matching directionality. And it will have high switching efficiency. Finally, it will be dynamically reconfigurable, supporting separation between spectral channels of up to hundreds of gigahertz. Here you see the simulation results. As we predicted, the eigenmode swap for the clockwise control loop. However, something we did not anticipate in the beginning is that the energy exchange is handedness dependent due to the asymmetric breakdown of adiabaticity, meaning that the eigenmodes will remain unchanged for the counterclockwise control loop. Such behavior was already reported in the literature in other platforms as well. In addition to the motivation I discussed in detail in the beginning of the presentation, these photonic systems, and specifically fibers, can also serve as sensors. Due to the limited time, I will briefly show only one example. I may be biased, but I think that fiber sensing is an amazing technology. Today, fiber sensors are being used in many applications, such as railway monitoring, oil and gas pipelines monitoring, gyroscope, current sensors, intrusion detection, acoustic sensors for submarines and oil wells, optrods, to list but a few. Here, we will focus on structural health monitoring. We are surrounded by structures, but do we know how they feel? Buildings collapse, bridges disintegrate, airplanes fall apart, wind turbines catch fire. The question is, can we anticipate a disaster? And the answer is yes. Yes, we can. We can achieve that by giving our structure a sensory system. Optical fiber is an outstanding candidate to achieve that. It can both sense and transmit the sense information by the same waveguide. It offers a low-loss link and thus can be used for long-range sensing. It is dielectric and as such is not affected by electromagnetic interference nor generates one. And it is very thin and low weight, easily embeddable in graphite fiber-based composites, as well as imprinted structures, or alternatively bonded to the surface of almost any material. In our work, we focused on aerospace applications, specifically on structures made of composite materials. Composite materials with superior strength to weight ratio are ubiquitously used in aerospace industry nowadays. The recently introduced Airbus A350 took the lead from the Boeing Dreamliner for the aircraft with the highest weight ratio of carbon fiber reinforced polymers, which was held at 50%. A typical composite laminate used in aerospace industry is composed of carbon fiber reinforced epoxy plies stacked with different orientations, in between which an optical fibers can be embedded without compromising its structural integrity. Therefore, fiber optic sensors are powerful tools for structural health monitoring of composite parts, as they can detect many critical defects which cannot be detected by other means. This is especially important during service. Of specific interest is damage detection at arbitrary location along the fiber under dynamic conditions. You can see here that the strain profile is different at a certain location because of the defect we intentionally introduced. In another project, we measured the dynamic deformation of rotating propeller blades. And finally, this is the best result achieved to date, to the best of my knowledge. We used Brilliant dynamic grating, which is a form of Brilliant enhanced 4V mixing that we saw before. And we also employed digital pulse compression techniques to measure 10 kHz vibrations with 2 centimeter spatial resolution and noise levels of nanostrains per square hertz. Here my talk comes to an end, but not before I thank all the wonderful people I had the privilege to work with during the years. And I want to thank you for your attention.
Okay, thank you for your talk.
Thank you.
Thanks a lot.
I'll be
Very
happy to take
interesting.
questions.
excuse me, anybody have questions? Anybody has questions?
Yeah, can I ask a question?
Of course.
Yeah, hi, this is
Hi.
Shmuel Sternclaw. Nice to hear you talk. I appreciate it very much. I enjoyed it. I'm not going to go through all the stuff you said throughout the talk. Although I have some questions, but just a brief question about your last topic. You mentioned fiber optic sensors with dynamic Brillouin gratings.
Mhm.
Can you give some kind of comparison of the sensitivity of dynamic Brillouin gratings versus, say, FBG sensor, FBG units, fiber Bragg grating, sensors that are attached to the fiber in terms of resolution, speed, stuff like that.
Yeah.
No.
Of course, of course. Actually, it's a difficult question, but it's very, very simple to answer, because the advantage of using Brillouin dynamic gratings or any type of nonlinear mixing in fibers to detect some sort of external perturbations is that you can use standard unmodified fibers. So, here I refer to fiber Bragg gratings as modifications. Okay, so the advantage is you can use unmodified fibers. On the other hand, fiber Bragg gratings is a commercial available technology. You can buy fibers off the shelf with I don't know, hundreds, even up to 1,000 of multiplexed fiber Bragg gratings along a single fiber. And the signal to noise ratio of measuring or analyzing the spectrum of fiber Bragg grating is clearly better. There is no doubt about that, because the intensity of the generated moving grating or acoustic wave that you can generate with the given fiber is much lower. I would say even with strongest pumps, you can generate refractive index perturbations which are 4 or 5 orders of magnitude lower than typical fiber Bragg grating. So clearly there is an advantage towards the fiber Bragg gratings. On the other hand, sorry, just let me finish, please.
No, go ahead. Finish up. Go ahead.
But something that fiber Bragg gratings cannot address is that they can't cover the entire length. So there will be dark areas along the fiber almost at all times. Okay, and the typical defects in this composite laminates may be sub-centimeters long in the fiber axis direction, and can be easily missed if they don't fall on top of the Bragg grating. Therefore, their ability to sense at arbitrary location is what makes these techniques appealing, in my opinion.
Okay, one more question, just a general question. You mentioned, like sort of in the beginning, of the applications in quantum communications. I didn't really see the connection between that topic and the work that you've been doing. Is there any? Can you expand on that a little bit? Or quantum sensing, quantum communications?
Yes, I can.
Yeah.
The two main topics that I covered in my talk that address those challenges basically give methods or give techniques of coherent control of propagating optical modes, such as their topological protection or asymmetric switching using the Non-Hermitian principles. Therefore, I expect that these techniques of coherent control of light, and in some constellations also of sound, can give tools for quantum applications. So these are not, let's say, straightforwardly applied, but it sets the stage for the transmission and processing of non-classical states of light. That's what I wanted to emphasize.
Okay, I'm not going to belabor this point. I'm just going to basically point out that, I mean, correct me if I'm wrong, but the effects that you described, which are very interesting effects, can also be described classically. I don't know if you really need quantum physics to describe these. And they're not pure quantum effects. They're classic effects that can obviously be described, you know, in a quantum way. Like all physics is basically quantum, but I mean, it's not really, you're not really taking advantage of the quantum revolution, right? I mean, you know, or something, you know.
Well, I am taking advantage in a sense because I want to use the devices that are being developed by foundry service providers. So therefore, I sort of benefiting from that. But again, here the answer may comprise two parts. The first part is, yes, of course you are right. All except maybe for one, but most of the effects that I described don't need to be formulated quantum mechanically. This is true. These are all classical effects. But I am very excited and very interested in this handshake between let's say the first quantum revolution, for example, all the principle of solid state physics, that using these analogies can be carried over to control light. What most excites me is that actually these approximations also hold not for the transport or for processing of classical information or optical information, but also for non-classical states. Therefore, it can be directly applied. For example, if you build such a topological system or a PT symmetric system and excited not with the classical laser light, but with a single photon source or entangled photon source, then you would expect similar dynamics. There's no difference. The assumption,
Right.
all assumptions hold.
Yeah, that's true. I agree. Okay, thank you.
You're welcome.
Arik, maybe you like to elaborate about this topological effects and how it is going to assist you in transmission of quantum information. Maybe this is the idea you like to elaborate for a few seconds. You were talking about topological effects. Can you express a little bit more about this?
Okay. Since well, it's a relatively young field of research. Yeah, this analogy between topological insulators and control of photonic states, or couple the graphs of photonic states. But up until this point, I was mainly concerned, like I said to Shmuel, for setting up the stage to observe this effect. But the quantum optics community is constantly looking for unique ways to control the propagation and the control of quantum information, specifically of photonic states.
Yeah, and one of them is topological effects.
Yeah.
Maybe you can guess how it goes into your fibers, or
yeah, for example, let's take the frequency encoded qubits as the example. There is no other way, to the best of my knowledge, to control spectrally separated photons with linear effects. So this is directly relevant. Now, as far as topology concerned, many recent example show that you can actually build a photonic structure or an array of waveguides or some sort of a photonic crystal and observe this topology and robust transfer, which is protected against disorder. Now, all this example, they prepare or build their device specifically for that purpose. What I suggest is that you can actually take standard and in some cases even already deployed infrastructures and observe similar effects and harness similar effects in order to enable the future quantum internet, computation, information processing. You can choose the buzzword that most appeal to you. So this is all done. I specialize in optomechanical effects, but other non-linearities, of course, can be considered as well. For example, brilliant scattering or other optomechanical effects are not parametric processes. Unlike for example, the Kerr effect, which is parametric, and actually using the Kerr effect for quantum control is preferred in this sense, at least at room temperature. But again, this is but the Kerr effect, for example, has other disadvantages because it's very wide band and it has poor spectral selectivity. Unlike, for example, optomechanical effects such as brilliant scattering, which is very narrow and provides better utilization of the spectrum. So these are the trade-offs, for example.
Thank you.
Again, I also want to say just one sentence. I didn't show you new physics. Okay, the physics that I've shown you has already been known in most of its parts from the beginning of last century, and some parts in the late let's say 80s of the previous century. But smart engineering and employing these principles can be used to build new devices and new technology.
Yeah. Okay, any further questions?
Well, I think it was enough. Thank you again, Arik.
Thank you very much.
Thank you very much, Arik.
Let's finish the seminar.